Hello friends, in this video we'll discuss a very important theory topic which is all about memory locations, addresses and operations. Let me tell you a very interesting fact. Whenever you run any program and your processor needs some data from main memory for that particular program, it never asks for the data from main memory directly. It will not say that send me this particular data. Rather than that, your processor will generate some address. What type of address? This address is nothing but the exact location of your main memory where actual data is present. Your main memory will get the address and it will decode the address, it will find the data, that data will be forwarded back to processor for the program. So this is how it actually works. So this kind of operations we'll discuss in this video. So let's start the video. Before we move on to the actual topic of the discussion, let me ask you a very simple question to all of you. Can you tell me the arrangement of main memory? I know most of you will answer it correctly. Yes, you are correct. Memory, I am talking about main memory or RAM. Memory is organized something like this. What you can see from this diagram. This diagram contains some cells, right? Small cells we have. How many cells are there? I don't know, n number of cells. This is how our actual memory looks like. Fine. What is memory? Memory is a hardware, right? So how it actually looks like, or what is the organization of our main memory? The organization of main memory is something like this, where I have n number of small cells which is organized like this. You got it? Now what are those cells all about? Each cell in my main memory can contain or can hold 1 bit of information. Is that clear? Now if I ask you, I have 8 GB of RAM or 8 GB of main memory, then how many such cells will be there in the main memory? You can easily count, right? Because each cell can contain 1 bit, then how many such cells will be there to hold 8 GB of information? You can easily count, right? If you have more memory, then there will be more number of cells like this. There will be many, right? 1 bit only. 1 cell is equals to 1 bit only. So there will be many such cells in your main memory. I hope you understood that, the basic organization. Now, the next thing. Suppose your processor wants something from main memory. It is asking for 50 and 60. It wants to add 50 and 60. So it wants to perform 50 plus 60, which is 110. Now this 50 and 60 are stored in your main memory and your processor is asking for that from the main memory. Remember, your processor will not ask the data directly from the memory. It will not say, memory give me 50, memory give me 60 so that I can add 50 plus 60. No. Rather than that, your processor will send some address to the memory, that memory, please give me something. I don't know what is there inside, but I have the address of the data. Whatever they are in that particular address, please send me that particular data. You understood that? Suppose in this example or in this diagram, I have 1 bit stored here in address number 12. So I am storing from 0 to n. So this is the 12th address I have. And here I have stored something. So whenever my memory needs something from this particular cell, it won't ask the data directly. Rather than that, it will send the address. What is the address? 12. So inside 12, whatever it's there, I don't know. It may be any information. Your processor will ask your memory that give me the data or the information, whatever present in the address number 12, please give it. And then your memory will give the data to processor to perform specific tasks. This is how it communicates. Fine, you understood that? Now, practically, whenever we have this kind of arrangements, means each cell contains only 1 bit, we know if I want to store a integer number, how many bits are necessary? So typically we need 4 bytes, right? To store one integer number. Say I want to store any integer number, say 25. To store this 25, how many such bits are necessary? 4 into 8, 32 bits are necessary for that, right? You understood that, right? For each integer number, I need 4 bytes. 4 bytes equals to how many bits? 1 byte equals to 8 bits, we know that. So 4 bytes means 32 bits. So just to store a simple integer number, I need 32 such cells. You understood that? These 32 cells will contain this value or data 25. You understood that? Now whenever your memory wants this data 25, then how it will send this address? Because this 25 is stored in so many cells. It's not a single cell now. It's not a single cell that I'll just send simply the address of a particular cell. I cannot, right? I have a group of cells now. So practically it's not possible to address our memory bitwise. This is not feasible, right? I cannot give so many addresses, and I know to store something I need more than one bit. So how it will be possible to give addresses for each bits like this? It's not possible. So what we do is, first thing, we divide the bits into some group of bytes. First thing, right? We know 8 bits equivalent to 1 byte. So this is 1 byte here. This is byte number 2, byte number 3, 4, 5, 6, 7, 8, 9. So I have the address of the bytes. You understood that? Next again, I told you, to store an integer number, I need 4 such bytes. So this complete cell is a byte now, right? So this is byte 0, this is byte 1, byte 2, byte 3. So these 4 bytes are necessary to store some integer number, say 25. Now again I have how many addresses or how many byte addresses I have? 4, right? So again, practically it's very difficult to assign something or assign addresses byte wise whenever you perform some operation. So what we do is, further we group bytes also. We group some bytes, and group of bytes are called a memory word. Please remember the term memory word, because in our subject COA we'll use this term memory word again and again in coming classes. Memory word is nothing but a collection of bytes. You understood that? What is bytes? Bytes are nothing but collection of bits. So now how we can do that? Say I am combining 4 bytes equivalent to 1 word. So this whole will become 1 word now. Fine? This is 1 word now. So in this, now if I store anything 25 here, easily my processor can send the word address, not the bit addresses or byte address, right? It will send that, give me something or whatever data you have in word number 0. So this word number 0 contains the number or value 25. So it will send that easily. Fine, you understood that, right? So if you understood these basic things, then this lecture will be very easy for you. So let's move on and see what are the other things we have in today's discussion. So whatever I said, exactly same thing we have. Memory consists of many millions of storage cells, each which can store 1 bit. I told you already. Data is usually accessed in n bit groups and is called word length. So whatever word I said, this is how the actual arrangements are made in main memory. So this is first word, second word, third word, like this. We divide the memory in n number of different words. In each word I will have some bytes. It depends on the system. In some system we have 4 bytes equivalent to 1 word. For some it may be 2 bytes. For some it may be even 8 bytes also in each word. Is that clear? Fine. Next, let's see what we have. 32-bit word length example. Again, whenever we say the system, we will say 32 bits. We won't say 4 byte memory. We will say 32 bits. 4 byte equals to 32 bits, right? So we say it as 32 bits length memory. Fine. So this is how it looks like. This is a word, and this word contains 4 bytes, and because each byte contains 8 bits, so total number of bits will be 32, 0 to 31. Fine. Now if I ask you to store some characters, so we know to store a single character we need only 1 byte, not 4 byte or 2 bytes, right? So in each word, how many such characters you can store now? 4, because I have 32 bits, which is equivalent to 4 bytes, and each word or each character can need only 1 byte, so I can store 4 characters easily in a 32-bit word length or 32-bit length words. You understood that, right? Now if I have a k-bit addresses memory, then it has 2 to the power k memory locations. Fine, you understood this 32-bit, right? If I ask you 64-bit, then total how many such addresses will be there that memory can access? It will be 2 to the power 64. If it is 16-bit, then 2 to the power 16. Total number of addresses will be 2 to the power 16. Now always the starting address is 0, then the last address will be what? If it is 16 bits, then the starting address will be 0 and the last address will be 2 to the power 16 minus 1, right? We know that, right? So like this we can get anything from our main memory. I hope this is clear for you. Now how to give the byte addresses? We know the word addresses now, right? I am going back to the previous diagram again. If this is the diagram, we know this is first word. I will put the word addresses, word 0, word 1, word 2, word 3, word 4, so on. Right? Now, how the actual addresses are given? It's not like word 0, word 1 will give. How to give that? It depends on the word length also. Because in some operation, we don't need the entire word, we need some bytes. Right? For that, we need the addresses of bytes also. Suppose I need something from word number 0, byte number 2. So memory will ask like this, give me something from word number 0, byte number 2. So that's why I need this byte addresses also, not only word addresses, right? So how to give this byte addresses? We have two different approaches for that. We'll see in this slide now. So two ways that byte addresses can be assigned across words. Two ways are there, as I told you. First one is called Big-endian. These two terms are very important to remember. Although this is theory, but it's very important for your any competitive exams or your final exam. One is Big-endian and one is little-endian. What is Big-endian and little-endian? These two terms are related with byte addresses only. What is byte addresses? Byte addresses are nothing but the addresses of bytes which are stored inside a word. You understood that? Suppose this is the main memory I have. I have n number of words. This is word 0, word 1, word 2, and I have n number of words. So how to assign the byte addresses? So there are two ways. First way is you put the addresses or you assign the addresses like this: 0, 1, 2, 3. Then you start with 4, 5, 6, 7, 8, 9, 10, 11 like this you can give. Fine. And another way is instead of starting from left to right, you can start from right to left. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 like this. So there are two ways. This is nothing but Big-endian. This is nothing but little-endian. Fine. Now, as of now, every time I said I have n number of words, word number 0, word number 1, 2, 3, 4, that, like that, right? But actually, it's not like that. Word numbers are totally depending on the byte addresses or byte, how many bytes are there. If this is word number 0, now next word address can be 1, 2, 3, 4. It depends on how many bytes are there. It's always not necessary that next word will be word 1. You understood that? So here word address is 4. Why? I have 4 bytes here. 0, 1, 2, 3. So 4 is the word address. And 4 is nothing but the first byte address also here. Right? If you arrange like this, same thing. 0, 1, 2, 3. This is the 0th word. And the next word address is 4. And here the last byte of the word is 4. For Big-endian, first byte is exactly same with the word address. In little-endian, the last byte or the MSB is exactly same with the word address here. 4, 4. You understood it, right? So Big-endian is nothing but an arrangement of the byte addresses where lower byte addresses are used for the most significant bytes of the word, whatever I said. And little-endian, opposite ordering, means lower byte addresses are used for the less significant bytes of the word. We have an example also. Let's see the example. It will be more clear for you. See, I have an example of some integer numbers. I am asking you to store these integer numbers 1, 53 and 26. I have given you 3 integer numbers 1, 53 and 26. And I am asking you, please store these 3 integer numbers in your main memory using Big-endian assignment and also using little-endian assignment. How it will look like? See, so in Big-endian, how it will look like? say I have available memory spaces 1000, 1000, 1001 and 1002. Fine. So what I will do, the first number 1 will be stored in memory location or memory word number 1000. Fine, 01. The next memory word, maybe it's given in the exam. If such kind of question you get, then you will be given the addresses also. What are the available spaces you have? So what are the available spaces I have? 1000, 1001 and 1002. And each address can contain one integer number. So what is the smallest address I have here? 1000. What is the leftmost digit, or what is the first digit I have? 1. So this 1 will be stored in 1000 only. Next number will be going for the next address, and the third one will be going for the third address. This is how Big-endian works. In little-endian, just the opposite one. The first number will be stored in the last available addresses. So what is the last available address we have? 1002. So here it will come. So in Big-endian, first available address or the smallest available address we have, but for the little-endian, the biggest available address or the last available address we have. Here 0, 53, 26, just the reverse one. I hope that's clear for you. So next is about word alignment. As I told you, if there are 16, I already discussed about this, right? How to assign the addresses for words. It depends on the number of bytes or the word length. If there are, say, 16 bit means how many words, how many bytes will be there? 2 bytes. If there are 2 bytes, then the word address will be like this: 0, 2, 4, 8, 4, 6, 8, like this. If there are 32 bits, means there are 4 bytes, then the word address will be 0, 4, 8, like that, right? If it is 64 bits, then 0, 8, 16, like this it will be. I have discussed this thing, right? So next is accessing numbers and characters. We know a number usually occupies one word. Why one word? I need 4 bytes to store a number. We know that integer numbers I am talking about. So 4 bytes equivalent to one word. This is a standard or typical word length, 4 bytes. Fine. By default it's 4 bytes. And for characters, as I told you, one byte is necessary to store a character. Means one word, one typical word can contain 4 different characters. Fine. Now memory operations. Now we'll come for the memory operations. Whenever you run any program, then I told you in the very first class or first video, the program, whatever you have written in high level, it will be converted back to low level languages or some set of instructions that can be understood by your machine, right? Now if you want to access something from your main memory, what you have to do is, first you have to load the thing, whatever data you have in the main memory and you want to access it. The particular data should be loaded to your registers first, right? So once it's there inside registers, then only you can process. Means you have to load from main memory to register first. To do that, we have a keyword in the instruction called load. Fine. So in load, you will copy the data to your register. Similarly, once your operation is done, now you want to send the data back to your main memory, maybe in some other location. What you have to do, you have to use the keyword called store. If you write store, that means now you have to transfer the data back from register to main memory. Load means from memory to register. Store means your operation is done. Now you can send it back to main memory. You understood that? Now there are some major operations whenever we have some set of instructions, which is nothing but a program, right? Once you run a program, we have a set of instructions. Now each instruction from the program are basically responsible in performing some of the major operations, which are, first one, data transfer, whatever I said, either from memory to processor or register, or from register to processor. Next, some arithmetic and logical operations on data. It may be that in your program there will be some arithmetic or logical operations. Third one is program sequencing and control. What is program sequencing and control? It will sequence the flow of the program. Suppose you want A equals to B plus C. So B should come first, C then next, then you have to perform A equals to B plus C. So there should be a proper sequencing, right? So this sequence controlling will be done through the instruction. Next is IO transfer. So once everything is done, you have to transfer back the result to your IO devices. Fine, I hope this is clear. Now to represent your instructions, I have two different notations. There are two different ways to write the instructions so that your computer can understand what you are trying to do with the program. First one is called RTN, register transfer notation. In register transfer notation, how to represent the instructions that you want to tell your processor to execute. Very simple, this is how we do. How? See what I am doing, this R1, this cursor symbol, then in square bracket LOC. This LOC is nothing but the memory location. You want to transfer some memory location to register R1. What is register and what are the general purpose register? I have already discussed in video number 1. Please go back and watch it if you have any doubt. So from main memory to register, if you want to transfer anything, this is how we write. That's it. This is the first code, first line. Fine. Suppose you want to perform R3 equals to R1 plus R2. How to represent in RTN? This is how we do. In square bracket R1 plus R2 and this cursor symbol goes to R3. Means in register R3, I am storing R1 and R2. R1 plus R2. Suppose you want to transfer something from R2 to main memory. Then what I will do? Say R3 to location. Say A, I am sending to location A. This is how we write. This is how RTN works. The second way is assembly language notation or ALT. So assembly language notation is very well known to you, right? So how to do that? This is how we write. Load, move, this is how we do, right? Load R1 LOC means whatever there in LOC in main memory will be transferred to location, register number R1, which is equivalent to R1, this cursor symbol lock in RTN. This is RTN, this is assembly language. Fine. If you want to represent in RTN, you have to write like this. If assembly, then you have to write like this. Fine. Similarly, if you want to add this R1, R2 and store it to R3, this is how we do. Add R3, R1, R2 means R3 equals to R1 plus R2. This is in RTN, this is in assembly. Most of the time, we will use assembly language only. Fine. In our future classes, we will see assembly language again and again to perform some operations. So that's it for this video. So in the next video, we'll discuss some more concepts.